Section 2.2 will be discussing graphs of functions. I will spend most of the time discussing piecewise functions, the graphs of piecewise functions, but also want to spend some time introducing several of the families of functions that we'll be seeing primarily throughout the course, and briefly revisit the vertical line test, which was already discussed in detail in section 2.1 with the lecture notes there. Okay. We'll start there. As a reminder, the vertical line test. Okay. The vertical line test is a method to checking to see if a graph of a relation happens to be in fact the graph of a function. Okay. It is based off of the definition of the function and the geometric or the graphical interpretation of that definition. If every or any vertical line crosses or intersects the graph of a relation, right, at most once, then the graph represents a function. So this is based off of the definition of a function, right? The function definition restated here. The function definition. Okay. For every input value in the domain, okay, input values are most commonly going to be x, but will not exclusively be x. Right? For instance, t is quite common as an input value as well, t expressing time in many cases. But for every input value in the domain, okay, there is exactly one output value, which generally would be y, but does not always have to be y, in the range. And our graphical interpretation of choosing an input value, okay, choosing an input value and then graphing it, consider the graph of x equals c, where c is a constant, our choice of an input value, right? That graph would be a vertical line, okay? The graph of x equals c, right, would be a vertical line, okay? And then the test says that if we put that graph of x equals c, superimpose it on over the graph of a relation, okay, there should be only one y value for that given x, right? And we can see how many y values we get by noting how many times our vertical line intersects or crosses the graph of the relation itself. Right? So, for example, let's take a look at the basic graph of y equals x squared, for example. And that's the graph of a parabola. Okay. I'll make it a little wider here. Okay. There we go. So, a parabola. Okay. So it has points on it such as, 0, 0, let's say 1, 1, right? Negative 1, 1, because negative 1 times negative 1 is 1, right? And so on and so forth, right? Then it would have 2, 4 on it. Okay. Negative 2, 4. Okay. Does this graph represent a function? Well, the test we apply is to choose a value of x, and for that value of x, draw a vertical line, right? And the equation of that vertical line would be x is equal to that choice that we made. For instance, maybe this is, I don't know, x is equal to 1/3, right? It's a choice of an x value, so we're choosing an input value. And we check to see how many times our vertical line intersects the relation that we're testing. If it only intersects in one location, that means there is only one possible y value for that given x, right? But we don't just test it for a single value of x. We actually want to test it for every possible input value x, that is throughout the entire domain. We have to test it for all the values throughout the domain. So it would be helpful maybe as an interpretation to think of scanning the graph with a vertical line, like we take a vertical line, and if we were to move it from the left to the right and scan the graph, we're checking to see that no matter where we look at it, no matter where we look at it in the scan, it is only ever intersecting the graph at most one time, right? It's okay if it doesn't intersect it at all. If it doesn't intersect the graph at all, then it means the chosen x value is not in the domain of the relation. We only have to check the values of x that are actually in the domain, all right? If the value of x was not in the domain, then we're not going to get a y value for it, all right? So we're really checking it for every x value, okay? So we're doing this for, right, every x in the domain, okay? And that's an infinite number of x values that we'd be doing for any continuous function. There's an infinite amount of values, uncountable number of values of x that we could choose to plug in to the relation. So it's easier to do this with a graph than it would be to do it, say, with a table of values, where we just, start listing numbers and plugging them in. Okay, because we'd never be done if we were just plugging numbers into the equation. Okay, we'd never run out of numbers to check. But by scanning the graph real quickly, we can see whether it passes this test or not. Okay, let's switch things around a little bit here. Okay, make a little bit of a change to our to the relation that we're looking at. Remember, a relation is just a correspondence between two sets. Here it's the set of x values versus the set of y values. So for instance, the relation over here is defined such that, for example, if x is equal to 2, then y will have to equal 4, and that's the way the relation is created right here. Well, what if we switch those around? What if we wanted to take a look at the relation x equals y squared? Now, x equals y squared, okay, is going to produce a graph for us that's going to be a parabola, but it's going to open outwards towards the right, like this. For example, it'll have the point 0, 0 on it at the origin, right? Because 0 squared is equal to 0, right? But what about if, let's choose the y value, right? If y is equal, start with y is equal to 1, okay? If y is equal to 1, then x is equal to 1 as well. Right? If y is equal to 2, right? If y is equal to 2, right, then the x value would be equal to 4. Right? So maybe 2, 3, 4, right? So this would be the point with coordinates 4, 2, for example. But also, if the y value is equal to -2, so this point would have coordinates 4, -2. So if we were to draw a vertical line representing the choice, right? The choice where x is equal to 4, right? That vertical line we would see would intersect the relation in more than one location, right? So in other words, right, we have chosen a value of x, right? We have chosen an x value, and it has corresponded to not one, but 2 y values. There are 2 potential outputs. So we would say that this is not a function of x. Okay, so x cannot be the input variable for this relation. This would also be true at a lot of other locations, right? If we drew a vertical line here, at some arbitrarily chosen location like that, it would also intersect in more than one location. If we drew, though, a vertical line out here, right, it doesn't intersect anywhere at all. But that's because this is not in the domain, right? X cannot be less than 0 for this given relation, right? Not when we're dealing with real numbers, right? All right, if x was equal to, let's say, -1, then that means, right? Then that means that y would have had to equal I, the imaginary number I. But that is not a real number, so we don't see any points over here where x is like, let's say, -1 or any negative number, for example, right? So we choose a value of x that is within the domain, and we check to see if it's possible that we could end up with more than one y value, okay, more than one output in the range. Okay, so we would declare that this relation here, okay, is not a function. More explicitly, it is not a function of x. Okay, so that's enough discussion with the vertical line test. You understand how to use it on when looking at the graph of a relation to determine whether something is a function of x or not a function of x. Okay, and also how it relates to the definition of the function itself. It is a graphical or a geometric interpretation of the definition of a function itself. Okay, so now let's take a look at the families of functions, a brief introduction to some of the families of functions. Okay, here are several of the families of functions. Okay, so we have linear functions, the power functions, root functions, which we can also call radicals, right? Reciprocal functions. Okay, the absolute value function, and finally the greatest integer function, which I'm not going to include in your homework set, but the greatest integer function is interesting in that it can be used to construct the step functions. So when there is a jump, okay, a jump discontinuity is what this would be called, and you will call that in your calculus class, a jump discontinuity, when there is an instantaneous leap, right, from one point to another over a gap, like that. Okay. Let's start with the linear functions. Okay, first off, they have the equation of a line. Right here we have it written in the slope-intercept form of the equation of a line, y equals mx plus b. And that's primarily the choice that is going to be made because we are replacing the output variable y with the notation of a function, f of x, right? So this represents the equation of a line, okay? We'll notice that this function right here, right, is a constant function, in fact, right? This would have the equation y is equal to b. In other words, that's where m, the slope, is equal to 0, right? And for this graph right here, well, this would specifically be the case where m happens to be greater than 0 because it is an increasing function. As we read this graph from left to right, if we were riding along this curve from left to right, we would be going uphill. Okay, so the y values are increasing as the x values increase, right? From any one point to another point, right, the y values increase while the x values also increase. We move up and to the right. Okay. If we had a graph that from the left to the right was instead going downhill, right, it would also describe a linear function. Okay, so we're crossing at B right here at the y-intercept, and this would be the case where m is less than 0, where the slope is less than 0. In fact, the only line relation that we do not see here in the linear functions would be a vertical line, right? So something like of the equation, let's say, sorry, let me get this red. Oh, I lost my line. Here we go. All right, so let's say we drew one of those vertical lines like we talked about with the vertical line test, right? Let's say that this is, how about 1, 2, 3. Let's say this is a graph with the equation like x is equal to 3, for instance, a vertical line. Does this represent the graph of a function? Why is it not represented here, right? It itself does not pass the vertical line test. Notice that this this relation right here has as its domain that x is equal to 3, right? 3 is the only value in its domain. But if we choose x is equal to 3, we get an uncountable number of y values, right? We get y is equal to 0, y is equal to 1, y is equal to 2, y is equal to 3, and so on and so forth. In the negative direction too, right? -1, and so on and so forth, right? This fails the vertical line test, and it fails it miserably, right? So we say that this would fail the vertical line test, okay? So the graph of a vertical line, okay, the graph of a vertical line is not a function itself. I'm going to abbreviate function with FCN right here, okay? So the linear functions would include horizontal lines, increasing lines, decreasing lines, and that's it, right? The linear functions do not include vertical lines because that would not be a function of x. Okay. All right, moving up now in exponents, in powers, from a power where of the variable, right, where x is to the power of 1, let's move up to where x is to the power of some other whole number for the time being, okay? Let's consider where it's x to the 2nd, or x to the 3rd, or x to the 4th, or x to the 5th, etc., etc., etc. Okay? The graphs of the power functions, switch that back to black. Okay. The power functions f of x is equal to x to the 2 times k, where I'm taking k is equal to 1, 2, 3, etc., etc. In other words, k is a natural number. Okay, by writing it like this, I'm saying that the exponent will always be an even number, right? So then 2k is always equal to an even number by setting it up that way, right? Those functions x to the 2k, are all going to have the shape of the parabola, like x squared and x to the 4th, for example. Okay, now let's see how they compare to each other. Okay, the x squared and the x to the 4th, right? They both increase towards infinity. Okay, they both increase towards where y is going to infinity as x goes to the negative infinity side or the positive infinity side, right? Because up on both sides. We can make them both sides go downwards, and when we look at transformations in section 2.6, all right, well, we can see, for example, by putting a negative sign in front of the leading term here, we can flip this whole thing upside down, okay? But just f of x equals x squared, right? It's going up on both ends right there, right? And x to the 4th also going up on both ends, right? But you see there's a slight difference in the way the graphs look, right? x to the 4th is kind of, hugging the x-axis a little bit more. It's a little more flat for a bit, and then it becomes more steep, okay? And where that change happens is between -1 and +1, okay? -1 and +1. Let's compare some values of x squared to x to the 4th and see why that's the case, okay? So let's take a look at x versus x squared versus x to the 4th, for example. Oh, and this will extend, when we go to like x to the 6th even, all right? And so on and so forth. Okay, so if x is equal to 0, all these will be 0, right? If x is equal to 1, right, well, all these will be 1. Okay, but what happens if like x is 1/2, right, or 0.5? Well, x squared is 1/2 squared, well, that's going to be 1/4. X to the 4th would be 1/2 to the 4th, well, that's 1/16. And notice 1/16 is less than 1/4, right? 1/16 is less than 1/4. So the y value, All right, these are all y values, right? This is y, this is a y, right? And this is going to be a y as well. The y value of x to the fourth is going to be less than the y value of x to the second when we choose x is equal to 1/2. So it's closer to the x-axis, because the x-axis would be where y is equal to 0, right? And then what happens when we go to x to the sixth? We're going to have 1 over 2 to the sixth, right? Well, 2 to the fourth was 16, 2 to the fifth will be 32, 2 to the sixth will be 64. So we got 1 over 64. So that's even less. So we can expect that the graph of y equals x to the sixth, right, for when x is equal to 1/2, the graph of y equals x to the sixth is even closer to the x-axis than either x to the fourth or x squared, and so on and so forth as we increase the power but keep an even power. Now, switching to a negative 1/2, we're just going to get the same results because of that even power, right? We're still going to get a 1/4, so we get symmetry here. It's the same on the to the left of the y-axis as it is to the right of the y-axis then. Okay, so that explains why, right, the graph of x to the fourth looks like it's a little closer to the x-axis than the graph of x squared. At least it is at 1/2 and negative 1/2, right? But at 1, we see for when x is equal to 1, they're all at the exact same location, right? So let's say I were to sketch, or try to sketch, right? Right? If I put like, you know, if I wanted to graph like y equals x squared, okay, for example, and also graph y equals x to the fourth, okay, maybe I should use a different color for that one. Oh, blue. Okay, x to the fourth is going to be hugging the axis a little more, and then it's going to go up like that. Sorry for the poor graphing here. Come on. Right? So y equals x to the fourth, right? X to the fourth is closer to the x-axis than x squared is. Okay? But they intersect each other, right? Where do they intersect each other? When the y value is 1. Okay, so at negative 1, 1 and positive 1, 1, they would intersect each other. And after that intersection, the function with the higher power or the higher degree ends up growing more steeply, right? As can be noticed by, let's say we chose a value that is greater than 1, like 2. At 2, x squared is equal to 4. Okay, when x is equal to 2, x squared is equal to 4, but x to the fourth, when x is equal to 2, x to the fourth would equal 16, right? So it switches, right? X to the fourth goes to be farther away from the x-axis than x squared was, and x to the sixth would be 64. And by symmetry, it would be the same in the other direction, right? If x is negative 2, we still get a 4, okay? 16 and 64. All right, so that's how they're going to compare. And x to the sixth would be even more extreme than x to the fourth was. Okay. Now, what about when there is an odd power, though, right? The odd powers for the functions. Okay, how about f of x is equal to x to the 2k minus 1, right? 2k minus 1. Okay, where again I'm thinking of defining k as a natural number. That's the counting numbers, 1, 2, 3, on and on and on. Like for instance, if k is equal to 1, then 2 times k minus 1 would be 2 minus 1, which is which is 1, right? That would just be a linear function. That would be this one right here, right? That would just be y is equal to x. Now, when k is equal to 2, we're going to get 2 times 2 minus 1, 4 minus 1, which is 3. So we're going to get x to the third. When k is equal to 3, we'd have 2 times 3, which is 6, minus 1 is 5. So we'd have x to the 5. So these are all going to be the odd exponents. 2k minus 1 will therefore always be an odd number. Right? So, for example, we'll take a look at x to the third. We've already taken a look at y equals x. That was a linear function, right? But x to the third looks like this. Okay? It sort of, kind of, maybe you might think it looks like it was going to be a parabola like this, except on the negative branch, sometimes I look at it like this, right? But on the negative branch, someone took this and they flipped that upside down instead. So they sort of took this part of the parabola and they flipped it downward instead. Okay, it's kind of like that. Okay, so this is x to the third. Compare that to x to the fifth. They're very similar shape, right? They both go up towards infinity as they go out to infinity, right? So they both go up, okay? They both go up and to the right as they go in this direction, right? Up and to the right, okay? But in the in this quadrant down here, in quadrant 3, quadrant 1, 2, 3, 4, quadrant 3, right? It is going down, okay, and to the left, as this was over here, down and to the left. Okay, we call this end behavior when we're checking to see what direction it is going, towards infinity or negative infinity, end behavior. Okay, more on that as we continue in the course. Okay, so they have the same end behavior, x to the third and x to the fifth, right? But where do they differ? Well, around near 0, and locally in that neighborhood around 0, again, the same way that x to the fourth and x to the squared were sort of similar but a little bit different in that region. Between -1 and +1, right? Again, between -1 and +1, okay? The higher the power, or the higher the degree, the more it's going to kind of hug the x-axis. It's going to stay closer to it for exactly the same reason as our analysis showed for the even powers as well. Okay? So that describes those functions. Okay? Let's move on to the root functions. You know, this is just an introduction to these power functions. We'll get further into that certainly in this course. Let's look at the root functions, okay, or the radicals. Okay, these can also be called the radicals. Okay, the nth root of x is what that says. Okay, so I'll write it a little larger out here. F of x is equal to the nth root of x, and that's for n is an element of the set of natural numbers. Okay, natural numbers are the counting numbers 1, 2, 3, etc., 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 expressed as a set there, and n is going to be greater or equal to 2. When n is equal to 2, we're dealing with a square root function, and that's this one right here. When n is equal to 3, it's a cube root. 4, it's a fourth root. 5, it would be a fifth root, and so on. Okay, let's see how they compare, right? We'll notice that n, which is called the index, okay, when the index, okay, if that is even, and of course we could express that by saying n is equal to 2 times k, right, where k is a natural number. That's one way that we could do it, just like we did over here. Okay, when n is even, right, we'll notice that we have a graph that starts at the origin but only moves outward, going up and to the right, and that's it. Okay, it moves up and it moves to the right whenever the index is even. Okay, and in fact, the domain, as we had discussed previously for these types of functions, I'm dealing with domains of functions, right? The domain for these even root radicals is that the radicand, which is the expression inside, okay, is greater or equal to 0. Okay, or in interval notation, that would be bracket 0 to infinity parenthesis. We can see that from the graph as well. There are no points to the left of the y-axis, right? That's because x is not allowed to be negative, right? So it doesn't exist over there. Okay. But what about, draw a line here. Okay. What about if n, the index, is instead odd? Like if it was 3 or 5, etc., etc. We could express it as 2k minus 1, where k is a natural number, right? So you have the cube root of x, we have the fifth root of x, okay? And those, right, have n behavior in both directions, right? It goes up and to the right, okay, but it also goes down and to the left in both cases. That's the n behavior, okay? And the domains, all right, for those odd indexed radical functions, the domain is all real numbers. So the interval from negative infinity to positive infinity. Okay. how do we compare when the index gets larger? You might notice that it is very much similar to what we were already noticing with the power functions. In fact, if we were to take any one, okay, of these functions and kind of flip it, rotate it, and flip it in a way, right, we would get representatives of these relations down here. For example, if you take the x squared function, okay, the x squared function, and if you were actually to kind of flip it so that it were opening to the right instead, like I showed on the earlier in this lecture note when I was showing the graph of x equals y squared. This is the graph of x equals y squared, except the bottom half of it has been eliminated so that we end up with a function. Okay, so consider the equation y equals the square root of x, after all, right? Y equals the square root of x. If you square both sides of that equation, you get x is equal to y squared, right? It is the same thing. The difference is, in order for this to be a function, we had to define that it was only true for where the y value was greater or equal to 0, right? Take a look at that for a second and notice that what that says right there is in fact that we have this graph right here. It is in fact a function of x, right? We looked at x equals y squared previously. We saw that that was a parabola on its side, but by restricting the y values to be greater or equal to 0, all right, it says that we eliminate the bottom half of this thing. And what we have, the graph that we're left with, is this graph right here, the graph of y equals the square root of x. Okay. The comparison between then the square root of x and the fourth root of x graph is very much like the comparison between x squared and x to the fourth. Okay. Okay. Until it gets to let's say y is equal to 1, for instance. Okay. From between 0 and 1, the function with the higher index is going to kind of hug the y-axis a little bit more, and then it's going to be more steep as it moves outward towards infinity. Similarly for the odd functions, right? They're going to, as the index gets higher, okay, the function is going to hug the y-axis a little bit more, okay? And then it's going to expand outward more rapidly once it gets outside of that interval -1 to 1. It's in the y direction instead of the x direction. Okay? The reciprocal functions. Okay, so 1 over x, for example, right? 1 over x. Okay, but also this would be, let's extend upon this, right? What would it look like if we had another, odd power? What if we wanted to graph, f of x is equal to 1 over x cubed, for instance, right? 1 over x cubed. Okay, so that is going to also look like this, right? It's going to be the same basic overall shape as y equals 1 over x, okay? It's not going to be too much different, okay? I'm not going to get a really good sketch of this right here. The same overall basic shape. There's a vertical asymptote, that is, there is a vertical line, which notes a location in the domain whereby the function is approaching it either to infinity or negative infinity. Okay, and that vertical asymptote is at x is equal to 0. It also has a horizontal asymptote at y equals 0. The horizontal asymptote is a horizontal line which the function also approaches as the x variable then goes to infinity or negative infinity. Okay, and we'll discuss asymptotes more later in the course as well. Now, the graph of f of x equals 1 over x squared also has a vertical asymptote at 0 and a horizontal asymptote at 0, but the graph is entirely north of the x-axis, and that's because we have an even power on the x, right? So, for instance, whereas the graph of y equals 1 over x, okay, would have, for example, would have a point on it at -1, -1, right? Because 1 over -1 is -1. The graph of 1 over x squared, right? When x is equal to -1, the y value is 1 over 1, right? So this is going to actually have the point negative 1, 1 on it instead. Okay, so you have the odd-powered reciprocal functions and the even-powered reciprocal functions. If we went to higher power, okay, of higher even powers, right, we're going to get stretches, right? It's going to like sort of shrink in towards the axes a little bit more, but have the same basic shape as this does right here. Okay, now on to absolute value function, the last of the families to discuss here, and the perfect transition to our next topic, piecewise functions. The absolute value function has this V shape to it. Right? This is the absolute value of x. We can look at transformations of that as well in a couple sections in the future. Okay, this basic function, first off, it is a function. It passes the vertical line test, right? Okay, but here's a way that we are most commonly going to be defining the absolute value function in mathematics in order to work with it in this class, in your calculus class, okay, and beyond that as well. The absolute value of x can be defined piecewise, okay? Piecewise in the following way. Take a look. It is on the left side, okay, on this left branch, it looks like the equation y equals negative x. Okay, it's like the slope is negative 1, okay, but it's only until it gets to 0. And once it gets to 0, then after 0, it changes and it becomes the graph of y equals x. For example, if x is equal to 3, right, if x is equal to 3, the absolute value of 3 is 3, right? So we would have the point 3, 3 on the graph, right? But if x was equal to, let's say, negative 3, right? If x is equal to negative 3, the absolute value would switch that to a positive 3. So we'd also have the point negative 3, 3 on the graph, right? The point 3, 3 is on the graph of y equals x, because the x and y are equal to each other, right? And the point negative 3, 3 could be found on the graph of y equals negative x, right? Because the opposite of negative 3 would be positive 3. For example, okay? So we define the absolute value of x piecewise. It is equal to the rule x, okay? As long as x is greater or equal to 0, it's equal to negative x, though, or the opposite of x whenever x is less than 0. Okay? I only want to define the function piecewise for when x is equal to 0. I only want to define it in one location. Okay, it would be the same thing if we said that it was less than or equal to 0 down here, but then eliminated the equal up here instead. It would still define the same absolute value function. Okay, but I wouldn't want to necessarily define it in both places like that. I just want to preserve that, algorithmically, that if we were to plug a value into this, okay, that it's only going to go to one of these two rules. Okay, even if like a computer device, if a software would want to do it as well, to be able to evaluate functions, like your calculator has functions on it, function keys. It has a square root key and, a logarithm key, and it has probably an absolute value function in it as well, and things like that. When you hit that key on your calculator, right, and you put an input in, it's expecting to put that input into a function, so it should only be looking for one rule to choose to plug it into. And it would confuse the device to try to plug a number into two separate locations sort of simultaneously. It's not designed to work that way. So by convention, we'll say that absolute value of x is equal to x when x is greater than or equal to 0, but absolute value of x is equal to negative x, or the opposite of x, when x is less than 0, right? So if x is a negative number, this will flip its sign back to the positive again. Okay, and the graph of that function is the V-shaped graph that we have right here. Okay, so now let's take a look at some more piecewise functions. Let's graph a piecewise function and do a couple examples like that. Okay, piecewise functions were introduced in the previous section, section 2.1, and we just saw another one there with absolute value. Okay, a piecewise function is again a function that has different rules over various segments of its domain. Okay, so the domain is going to be split, and over the subintervals of the domain, however it's split, the rule of the function is going to change. Okay, So graph the piecewise function. Okay, or the rule may change. Okay, so here's an example. Let's call one g of x, right? We've been calling functions f of x all day. Okay, so let's call this one g of x. G of x is equal to, let's see, 3x plus 2, okay, if x is less than negative 1, okay, but g of x is equal to 2 minus x, okay, let's say, if x is greater or equal to negative 1. And it's just an example, okay. Okay, what is this going to look like as a graph? Okay, well, we would consider the graphs of two other relations or functions in this case. Consider the graph of y equals 3x plus 2, okay, but we only want x to be less than negative 1 on that graph. And consider the graph of y equals 2 minus x, but we want x to be greater or equal to negative 1. Each of these are linear. They're linear functions, and we know how to graph lines really well. Okay, so I'm going to start by setting up a grid here, okay, and filling in a table of values as well. That would be helpful for some point plotting. Okay. We know the shape of linear functions, right? You know, we know, for instance, they're both in slope-intercept form, basically, right? This is a slope is equal to 3 here, so this is going to be an increasing function. It's going to go in that direction up and towards the right. It's going to have a y-intercept of 2. This is y equals negative x plus 2, so this has a negative slope. Okay, so this one has a negative slope, so it's going to go downhill towards the right, and it's going to have a y-intercept of 2 as well. Okay, I don't want the entire graph of each of these. Like, I don't want to go graph each of these from negative infinity to positive infinity, because what we want is a function that is partly like this, but also partly like that, right? As defined by the by the segments of the domain that were chosen here, okay, the subintervals. Okay, so I'm going to do a table of values here. X versus g of x, right? The function we're actually trying to analyze. Okay, and like, say for instance we choose x is equal to 0, right? We plug x is equal to 0 into this function, and then by looking at these inequalities here, we can decide in which rule to plug the 0 into, right? Well, 0 is greater than negative 1, right? So it gets plugged into this branch right here, right? When x is equal to 0. So in that case, we get 2 minus 0, and that equals 2. So the graph of g of x, okay, is going to have the point 0, 2 on it, first of all. Okay, so 1, 2, I'll plot a point there. We at least have the point 0, 2. Okay, now what happens if, let's say, we have x is equal to 1, right? If x is equal to 1, well, that's still greater than negative 1, so it gets plugged into this branch again, right? So when x is equal to 1, we have 2 minus 1, which is 1. So that means the point 1, 1, okay, is going to be on the graph, right? Both of these points are on the graph of y equals 2 minus x, because that was the rule that we used. So we know that these are going to be connected in a line, okay? Now, that line should not, for this example, should not extend indefinitely in both directions, okay? But how far does it extend in both directions? Well, x can be any value greater than negative 1, right? So if we were to increase the value of x to 2 and 3 and 4, etc., 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 right, we should still be on this trajectory, right? So for instance, if x is equal to 2, we'll be at 2 minus 2 is equal to 0, right? So we'll be at the point 2, 0, and so on and so forth, right? It continues out to the right because x can be any number greater than negative 1, and we'd still be on that trajectory right there. Okay, but how far to the left? It only goes as far as negative 1. So let's see what happens when x is negative 1. When x is negative 1, okay, we're going to be still in this rule right here, and we would have 2 minus negative 1, and that equals 3. So the point negative 1, 3, okay, would be a point as well. Is that point open or closed? I now need to consider that here in 2 dimensions, right? Is it a filled-in point, a solid point, or an open point? Okay, that point is because we have x can equal 1 on this branch right here. Because we have that, okay, then this is going to be a closed point, okay, a closed point, okay, and that completes this trajectory right here. Okay, that closed point is at the location -1, 3, right there. Okay. Okay, now what happens when we start creeping to values that are less than -1? Okay, now what does it mean to be less than -1? Does that mean we start at -2? Not necessarily. I mean, what if we had like -1.001, right? That's less than -1, isn't it? Right? So that would be a point, okay? But instead of considering like precisely that, okay, you know, because that would be hard for me to graph here, already harder than what I'm already graphing here, I'm going to write the notation in this way. I'm going to write that I'm choosing x to be close to -1, but a little bit less than -1. And to make it less than -1, I'm going to put a little minus sign here where you would normally see the exponent. Sorry. Little minus sign here where we'd expect to normally see the exponent. Okay, so this is notation, okay, and this is to express closeness to a value. Okay, consider if x is close to the value c, okay, if x is close to c, okay, then if we say that x, let's say, is equal to c with a little minus, okay, means x is just a little bit less than c, okay? X is less than c, but very close. For instance, maybe x is something like sorry, I can't do a specific number here, right? But up here, it would be like saying that we're saying that x is, like I just wrote, -1.00000000001 or something like that, right? Some number that's really close to -1, but just a little bit less than -1. And that's what that notation means. Okay, to say that x is equal to c, but with a little plus sign here instead, where the exponent would normally be, right, means the other direction. Means that x is greater than c, but again, that it is very close. Okay, so if I had a -1 with a little plus sign there, okay, for example, like -1 with a little plus sign, could mean that I'm talking about a number like -0.9999999, right? A number like that, which is just a little bit larger than -1, for example. Okay, so this allows me to investigate what's going to happen if x is about -1, okay, but technically is actually a little bit less than -1, and that allows us to investigate what's happening here very, very close to -1. As we're very, very close to -1, we would be in this branch 3 times -1 plus 2, 3 times -1 plus 2, okay, is what? -3 plus 2 is -1. This is the y value now, okay? The y value now. So the point with coordinates -1, -1, okay, is a point of interest to us. So -1, -1 is a point of interest. Furthermore, the point at the location -1, -1, is it open or closed? Because we do not include equality right here, okay, that x can't actually equal to -1, okay, that's going to have to be an open point right there, right? That's because we couldn't actually plug -1 into this. It was supposed to get plugged into the other branch. But we had to consider values of x that were really close to -1. So this is going to be an open point right here. So we're kind of testing both rules at -1, because -1 is the crossover. But one of those two rules will output a closed point. The other one will output an open point for the value when x is equal to -1. Okay, right? So if x is equal to -1 in this branch, it's going to be an open point. But if x is equal to -1 along this branch, it's going to be a closed point that we're going to graph, okay, in 2 dimensions. How do we graph an open point? With an open circle, all right? Right, with an open circle enclosing that location right there. Okay? Now what's going to happen? Let's stay on that branch. Where are we on 3x plus 2? Let's choose another number that's less than -1. Because this is just a line, y equals 3x plus 2, we really only need one more clear point, because 2 points is sufficient in order to define the direction of a line. Right? So one more point on a line would be enough. By the way, if we were graphing something like 3x squared plus 2, like a parabola, right, we'd want to increase the number of points. 2 points would not be enough to define a parabola precisely. We would want at least 3 points, okay? And we want to go through a turning around point. We'd hope that one of them was maybe the vertex, and at least one to the left of the vertex and one to the right of the vertex. For example, the higher the degree goes, the more points we really are going to need in order to actually define where that graph really exists, okay? But when it's a linear function, when it's a line, 2 points, okay, 2 points should be sufficient. So we have 1 point here at -1, -1, right, and it's open. Okay, and now another point can be found by choosing, let's say I choose x is equal to -2. If x is equal to -2, we have 3 times -2 plus 2, right? That's what, so that's going to be -6 plus 2 is -4. So this is the point with location -2, -4. So that's -1, -2, -3, -4. Okay, and then this would be -2 right here. So right about around here, we're going to have this point right here. I'll label that -2, -4. Okay, so our graph emanates from this open circle. All right, try to get more center. Here we go. From the open circle, and it moves in this direction. In other words, right, this is along a linear trajectory that has a positive slope, right? This is the 3x plus 2 portion of this piecewise function. And this has the negative slope. This is the 2 minus x portion of our piecewise function. Now, notice that this graph, when taken in entirety, all right, this is important here for when I'm checking your graphs that you submit to me on tests, like when you create them by hand and submit to me your hand-drawn piecewise function graphs. I should be able to check on it and see that it passes the vertical line test. This passes the vertical line test, right? It must pass, right, the vertical line test in order for it to be a function, okay? When might it not pass the vertical line test? Well, if someone were to, if you were to do, for instance, something like this, if you were to allow this line to extend in this direction indefinitely, it fails the vertical line test. How? Because now I can draw a vertical line someplace like right here, and it hits here and here. But these are both supposed to be on the same function, right? Because we have defined one function called g of x, right? So this would fail the vertical line test, okay? This passes the vertical line. It even passes the vertical line test here. Notice that if we were to draw the vertical line right here, it still passes because it only actually hits the graph at this location. It doesn't hit the graph here because it's open. Okay. All right, so here's your complete graph for that g of x. Okay, I want to try maybe one more example like this, and then do something slightly different. Okay. Again, graph the piecewise function. Okay, yeah, f of x is equal to, this one's going to have 3 branches on it. That's one difference. So the first branch will just be the constant 4, okay, and that'll be if x is less than -2. The second branch will do something quadratic. How about x squared? Just the basic x squared graph for this example. Okay. and that can be for negative 2 is less than or equal to x, which is less than or equal to 2. And then finally, how about a linear branch, okay, or linear piece? 6 minus x, right, if x is greater than 2. Okay, let's set up a grid here. X-axis, y-axis, okay. The transition points would be at negative 2 and at positive 2. So we want to be testing around those locations, certainly. We want to test from the left and from the right, right? So we might want to consider what happens if x is a little bit less than negative 2. What happens if x is actually equal to negative 2, for example, right? Because it's equal to negative 2 along this branch here, but it's a little bit less than negative 2. Well, it's less than negative 2, right? But at very least, it is a little bit less than negative 2 there. We want to test where x is equal to positive 2. Will be on this branch. Then we want to test also where x is just a little bit more than positive 2 as well, so that we can be testing on this branch right here. Okay, so that we can see where it's open and where it's closed on the graph. We'll put this whole thing together. Okay, so we got x and we have f of x. Okay, let's start with something that's less than negative 2. Okay, now no matter what value we choose, less than negative 2, it doesn't matter, right? The function is constant. No matter what value of x we choose, if it's less than negative 2, the output is simply 4. Right? Right up to where we are just about negative 2. That means if we were to plug in a number that is just a little bit less than negative 2, right? Just a little bit less than negative 2, we're going to get 4. Okay? So this is heading towards the point negative 2, 4. Okay? But along that trajectory, that would be open. Okay? So we can start there. All right? We can start there. So 1, 2. So here's negative 2. 1, 2, 3, 4. Okay, so negative 2, 4. I'm going to put an open point there. Okay, and then we have the constant function y equals 4 extending outward to the left. All right, there we go. All right, and so that's got a point on it like negative 3, 4 as well, right? So negative 3, 4 is there, and negative 2, 4 is there, but it is open. Okay. It needs to be clear on your graph whether the end point is open or closed. Okay, so because if I don't want it to be arbitrary. I want to be able to know if it's an open or a closed, or it might get marked wrong otherwise. Let's see what happens after what happens when we get to negative 2, right? That's what we can do, right? If x is equal to negative 2 itself, then we use the square function. Negative 2 squared, and that's equal to 4. And that is going to be a closed point. Well, it looks like we have the exact same point, right? We do. Okay? Negative 2, 4, again. Okay, well, that allows us to go to the same location then and fill it in. Okay, it becomes a solid point now because we are on the middle branch of this piecewise function. Okay, then what happens? Well, what about at negative 1? At negative 1, we get negative 1 squared, which is equal to 1. Okay, so negative 1, 1. Okay, so that's right there. And of course, we have something that's shaped like a parabola. Right, so I'm going to kind of try to get a curve into this. It's going to go through 0, 0. Right, I know that it's going to hit there eventually as well. Let's see what I can do here. Here you go. There's not too bad of a curve. It's okay. Right, we get 0. 0 squared is 0. Right, and then by symmetry, it's going to look the same on the other side as well. By the way, right, it's going to be 1. 1 squared is 1. 2. 2 squared is 4. All right, y equals x squared is symmetric about the y-axis. Okay, so we have this point right here at 1, 1. Okay, and we have 2, 4, which is a closed, by the way, closed point as well because x can equal 2 along that branch. Okay, so I'll try to get a parabola, trying to get some symmetry going on here. All right, so like that, right? So it goes through 0, 0, right? 1, 1, negative 1, 1. All right, we've got 2, 4, and 0, 0. Okay, now what happens if x is just a little bit more than 2? Okay, so for example, what if x is like 2.00001, right? Something like that, approximately that or whatever. Just a little bit more than 2. Okay, then we would also be along this branch, and we'd be looking at 6 minus that number that's just a little bit more than 2, but very, very close to 2, right? So 6 minus 2 is equal to, well, 4. Okay, now, on this branch itself, this point with coordinates 2, 4 would actually be open. Okay, it would be an open point because x can't actually equal 2 there, but like it was on the other side, it was the same location of a closed point that we already included, right? So we have an open point on top of a closed point, so it just looks to us like it was closed all along. All right. All right, this branch is a linear branch, right? It is linear. So we just need one more well-defined point, okay, for an x that is greater than 2, and we'll be able to graph the trajectory. So let's say x is equal to 3. Then we have 6 minus 3, which is equal to 3. Okay, so we have the point 3, 3 at that location right there. Okay, and we can continue with this if we wanted. We could choose x is equal to 4, 5, 6. You know, at x equals 6, we know, for instance, that this is going to be, what, 6 minus 6 is equal to 0. If we wanted to continue this outward, we could. Okay, but this is going to move in a path like so. Okay, and it's going to cross at the location 6, 0. Okay, and as was mentioned in the graph previous to this, right, this entire graph, okay, must pass the vertical line test because it was a function from the start, right? This thing was a function, okay? So we verify when looking at our completed graph that it passes the vertical line test. This is in fact a function. All right. So I have one more example that I want to do from this section, which like you have a couple examples of in the homework, okay, and that's reverse engineering of one of these examples. What if we are given the graph of a piecewise function? This is just one example, right? Given a graph, and we need to determine the formula or the set of rules, as well as the subintervals of the domain for which those rules are defined. Okay, so let's do this one. Okay, let's give this one a name. I'm going to call this one f of x. Okay. So what's the rule? Well, we can see already the families that it belongs to, right? This is linear, right? This is linear, and this is linear. Okay, each of the branches. Okay, so we need 3 linear functions. Now, every linear function can be defined by if we can find 2 points using the graph. If we can find 2 points that we know for sure what the coordinates are of those 2 points, we have all the information we need to build a linear function, right? Because we can find the slope and we can find the y-intercept. Even though this line, for instance, doesn't actually cross the y-axis, we know that if we were to extend it outward to infinity, it would eventually cross, right? Now, what's the slope of this line here? We can see that the slope, just by looking at it, the slope is 0. And the y-intercept, if it continued in that direction, the y-intercept is going to be 2, right? So we already have the first piece, okay, pretty much by inspection. There wasn't a lot of work to have to do there. I mean, we could make it more work than that. We could say there was actually the points, for instance, like what? Negative 4, 2 is a point, and negative 3, 2 is a point, right? And then we can do the whole y2 minus y1 over x2 minus x1 with these two, and we're going to end up with 0. We're going to reach the same conclusion here anyway. Okay, there will be time for us to do that when we have a more complicated looking line. We'll do that on this piece right here, why not? Okay, So the first branch right here, starting from the left, I'm going to work from the left to the right, by the way. Okay, this has the equation y is equal to 0x plus 2. In other words, y is equal to 2. Okay, so f of x is equal to 2. That's y is equal to 2. Okay, and that's on what branch? That's if x is any value, right? These are the x values, any value to the left of -1 or equal to -1. So if x is less than or equal to -1. Okay, it would be also similarly easy to find the equation for this one right here, right? For this line right here, we see again that the slope is equal to 0, and if we were to extend it towards the y-axis, we can see that b is equal to -1, right? So over here we have the equation y is equal to 0x minus 1, or y is equal to -1. Okay, I'm going to put that one at the bottom here so I can list these from top to bottom is from left to right. So down here I'm going to have f of x is equal to -1, and that's if x in this case would be anything more than 2, but notice not equal to 2 when we're on that branch. So this is if x is greater than 2. Okay. All right, now for this piece right here, right, it is linear, so we need 2 points, and we'll be able to define it. Also, we can figure out what the subinterval of the domain is that we need. To the left edge, even though it's open here, the left edge would be where x is -1. Okay, so I already have that we have -1, okay, to the left, and the x values along this trajectory, okay, are as large as 2, and they include 2 because that's a closed point right there. So -1 is less than x, which is less than or equal to 2, right? So we go from open on the left to closed on the right when we're along this segment. Now we need to figure out the mx plus b, right? The mx plus b rule for this line. And that we can do by locating specific points, as long as we know the exact coordinates of those points. We don't want to guess at what the points are for this example. We're not being asked to guess. So we should find out to where it locks into the grid at a couple of locations. So for example, this point right here looks like it has coordinates 0, 2. And this point right here, which is included, and this point right here is another one, and this point right here, right? Any of those, they're along the same trajectory. We have the point 2, 0, okay, as another example. These 2 points then define a unique line. The unique line defined by those 2 points, right, we can find the value of m, which is equal to y2 minus y1 over x2 minus x1, okay? Again, right, I'll write the formula, y2 minus y1 over x2 minus x1, which in this case, right, like if I call this one y2 to start this off, would be 0 minus 2, because then this would be y1, over 2, right, because this would be x2, minus 0, because this would be x1, right? So what's that? So that's -2 over 2, which is equal to -1, right? So we have the slope is equal to -1 along this trajectory right here. So that gives us y is equal to -1 times x, and then plus b. Well, what's b? We're given it right here from the graph, so we don't have to do anything else, right? We've already, we looked at in the geometry of lines how in general, if we don't know what the y-intercept is, but we are only given 2 points, we can still find out what the y-intercept is, right? We can, like, for instance, write the equation y equals mx plus b, where we can plug in the value of m along with an x and a y that we already have, right? Well, that won't be too obvious, but like an x and a y that we already have, like 2, 0, right? We can plug those 3 things in, and then we're left with just solving for b. So -2 added to the other side, 2 is equal to b, right? So we could do it that way as well if we couldn't tell from looking at the graph what it is. Okay, we just need 2 points in order to be able to define the equation of a line uniquely, right? And we can get it in y equals mx plus b form. So we have -x plus 2. So we can write -x plus 2 right here. Well, I can commute these 2 terms to save a little space and not write that plus sign. I can just write 2 minus x. 2 minus x is the same as -x plus 2. Okay, and that completes the exercise then. all right, for this given graph. Okay, so we did it piece by piece, all right, paid attention to the to where the open and the closed points were, where there were jump discontinuities in this case. In other words, where we had the transition values of x, where we were transitioning from one segment to another segment. Okay, here the transitions were from -1, okay, and 2 as well. Okay, that's it for this section. You can check out the homework and let me know if you have any questions on that. Okay, take care.